On a quiet night in July 2025, while most of the world slept, a robotic telescope in Atacama Desert was doing what it does best, scanning the southern sky for anything that might threaten Earth. The Atlas survey, short for Asteroid Terrestrial Impact Last Alert System, had been faithfully cataloguing space rocks for years, building humanity's defense against cosmic impacts. At 14:49 Universal Time on July 1st, something appeared in the data that made the computer algorithms pause. A faint dot of light was moving across the star field, but not in the way asteroids usually move. This dot was traveling too fast and in the wrong direction entirely. Within hours, astronomers around the world were pointing their telescopes toward this peculiar visitor. The numbers that came back were staggering. The object was racing through space at over 130,000 miles per hour, fast enough to cross the United States in under 3 minutes. But speed wasn't the only strange thing about this cosmic wanderer. The mathematics of orbital mechanics told a clear story. This visitor was following what scientists call a hyperbolic trajectory, meaning it was moving so fast that our sun's gravity could never capture it. Unlike the asteroids and comets born in our solar system, which follow elliptical paths that eventually bring them back, this object was just passing through. It had come from somewhere else entirely. They designated it C divided by 2025 N1 Atlas, but to astronomers studying visitors from other star systems, it quickly became known simply as 3I Atlas, the third confirmed interstellar object ever detected. The I stood for interstellar, marking it as a messenger from the space between stars. The discovery felt almost routine at first. Advanced sky surveys had been finding these interstellar visitors every few years, since 2017, but as the initial observations poured in from telescopes around the globe, astronomers realized they were looking at something that didn't fit their expectations of what an interstellar rock should look like. This wasn't just a cold, dead fragment drifting through the cosmic void. As 3I Atlas approached our sun, something remarkable was happening. The visitor was waking up, developing a faint, fuzzy atmosphere as ancient ices began to sublimate in the warming starlight. After millions of years in the frozen depths of interstellar space, this cosmic wanderer was coming alive. The timing seemed almost deliberate. 3I Atlas was approaching at just the right angle and distance for Earth's telescopes to study it in detail. For the next several months, humanity would have a rare opportunity to examine a piece of another star system, carrying chemical signatures from alien worlds we could never hope to visit. But first, scientists had to figure out why this visitor was behaving so strangely, and what its unusual chemistry might reveal about the mysterious realm between the stars. To understand why 3I Atlas captured the attention of astronomers worldwide, we need to meet its predecessors, the two interstellar visitors that had prepared scientists for this moment, yet somehow failed to prepare them for what they would actually see. The first confirmed interstellar object, 1I Oumuamua, arrived in October 2017, like a cosmic riddle wrapped in starlight. Hawaiian astronomers spotted it streaking away from the sun, having already completed its closest approach, while humanity remained unaware. Oumuamua was strange in every way possible, elongated like a cosmic cigar, tumbling end over end, and showing no signs of the gas and dust that typically surround active comets. But Oumuamua's strangest feature was invisible to the eye. As it raced away from our sun, the object began accelerating slightly, pushed by forces that shouldn't exist for a simple rock. The acceleration was tiny, about 1/10,000th of Earth's gravity, but it was real and measurable. Scientists proposed various explanations, from outgassing hydrogen to solar radiation pressure, but none fully satisfied the mystery. Then came 2I divided by Borisov in August 2019, discovered by amateur astronomer Gennady Borisov from his backyard observatory in Crimea. If Oumuamua was the mysterious stranger, Borisov was the friendly neighbor who behaved exactly as expected. It developed a proper comet tail, outgassed water vapor and dust, and followed predictable physics throughout its journey past the Sunday. Borisov carried its own chemical surprise, though an abundance of carbon monoxide far exceeding anything seen in our solar system's comets. This suggested formation in an exceptionally cold environment, perhaps around a star with an extended disk of icy material. Still, Borisov felt familiar, like meeting a comet from home that happened to speak with a foreign accent. These two visitors established a pattern that astronomers thought they understood. Interstellar objects would be either mysterious and inactive, like Oumuamua, or normal and well-behaved, like Borisov. They seemed to sample different extremes of what interstellar space might contain. 3. I-Atlas arrived to shatter these comfortable categories. It showed activity like Borisov, developing a fuzzy atmosphere of gas and dust, but its chemistry was dominated by carbon dioxide rather than water or carbon monoxide, a completely different molecular signature that spoke of formation conditions unlike either of its predecessors. The progression from Oumuamua to Borisov to 3I-Atlas revealed something profound about the space between stars. Rather than being filled with similar debris from similar processes, the galaxy appeared to harbor an extraordinary diversity of materials and formation environments. Each visitor was like a core sample from a different alien world. With just 3 examples, astronomers were already seeing 3 completely different personalities. This suggested that the universe might be far more chemically diverse than anyone had imagined, and that our theories about planetary formation might need significant revision. Understanding how we know 3I-Atlas comes from another star system requires diving into the elegant mathematics that govern how objects move through space. But the story is simpler than the equations might suggest. It's about reading the cosmic speedometer that every moving object carries in its trajectory. When astronomers track an object across the night sky, they're essentially watching it trace a path through 3-dimensional space. Objects born in our solar system follow elliptical orbits, like cosmic racetracks that eventually bring them back to where they started. These bound objects have orbital eccentricities less than 1, a mathematical way of describing how stretched or circular their paths appear. 3. I-Atlas was different from the moment astronomers calculated its orbit. The object showed an eccentricity of approximately 1.7, placing it firmly in hyperbolic territory. This meant it was following an open curve through space, a path that stretches toward infinity rather than looping back on itself. No amount of gravitational influence from our sun could change this fundamental fact, but eccentricity alone doesn't tell the complete story. The truly diagnostic measurement is called the hyperbolic excess velocity, essentially the speed an object would have if it were infinitely far from the sun's gravitational influence. For objects born in our solar system, this velocity is 0 because they're gravitationally bound and will eventually return. 3. I-Atlas showed a hyperbolic excess velocity of roughly 25 kilometers per second. To put this in perspective, Earth orbits the Sun at about 30 kilometers per second. This interstellar visitor was moving nearly as fast relative to our entire solar system as our planet moves around our star. That's the signature of origin in a completely different gravitational environment. The visitor's incredible speed at 130,000 miles per hour wasn't just impressive, it was diagnostic. This velocity represents the accumulated energy of gravitational encounters with other stars during its journey through the galaxy. Each close passage by a stellar system could add or subtract energy, gradually accelerating the object over millions of years of wandering. The trajectory calculations also revealed something poetic about 3I-Atlas's path through our solar system. Its closest approach to the Sun, called perihelion, would occur on October 29th, at a distance of roughly 130 million kilometers, threading the needle between Earth and Mars with almost surgical precision. This geometry meant that 3I-Atlas would experience intense solar heating during its closest approach, potentially triggering dramatic changes in its activity and composition. The visitor was essentially scheduling its own scientific climax at the point where our Sun's energy could best reveal its hidden chemistry. The orbital mechanics told astronomers exactly when they could observe this cosmic performance and when they would lose their chance forever. 3. I-Atlas would remain visible until early 2026, after which it would fade beyond detection limits and return to the interstellar medium, carrying its secrets back to the space between stars. When the Hubble Space Telescope first turned its unblinking eye toward 3I Atlas on July 21, 2025, it captured an image that perfectly embodied the challenge of studying interstellar visitors. The photograph showed a fuzzy, teardrop-shaped cloud of light against the star-scattered darkness, beautiful, mysterious, and frustratingly unresolved. The nucleus of 3I Atlas, the solid heart of this cosmic wanderer, remained hidden within its own glowing atmosphere. Despite Hubble's extraordinary resolution, the object appeared as nothing more than a bright point source surrounded by a fuzzy envelope called a coma. This wasn't a failure of the telescope, it was simply the reality of studying something so small and distant. What Hubble could determine were the size limits. Based on the object's brightness and assumptions about how it reflected sunlight, astronomers estimated the nucleus was somewhere between 320 meters and 5.6 kilometers across. That's an enormous range, the difference between a large building and a small city. Without being able to resolve the object directly, scientists were essentially making educated guesses about its fundamental properties. The coma itself told a more accessible story. This ghostly atmosphere, stretching thousands of kilometers in every direction, was created by solar energy, sublimating ancient ices that had been frozen for millions of years. The process was like watching a cosmic awakening dormant materials responding to our sun's warmth by transforming directly from solid to gas. Hubble's tracking capabilities created one of the mission's most striking images. By following 3I Atlas's motion against the stellar background, the telescope made the stars themselves appear as bright streaks while keeping the comet perfectly centered. The result looked like the visitor was flying through a tunnel of light, emphasizing its alien nature among the fixed points of our local stellar neighborhood. The dust production rates that Hubble measured were surprisingly normal for a comet at 3I Atlas's distance from the Sunday. This might seem reassuring evidence of predictable, familiar physics, but there was a crucial difference. This object had spent millions of years exposed to interstellar radiation that should have fundamentally altered its surface chemistry. Yet it was behaving like a fresh comet on its first passage through the inner solar system. Perhaps most puzzling was what Hubble couldn't see clearly. The anti-solar tail, the stream of material blown away from the sun by radiation pressure, was remarkably subtle. Most active comets develop prominent tails that are easily visible in amateur telescopes, but 3I Atlas seemed determined to keep a low profile. This subtlety would persist until late August, when deeper images from ground-based telescopes finally confirmed what theory demanded. Yes, 3I Atlas did have a tail, but it was playing by its own rules of visibility. The geometry suggested either unusually large dust grains that resisted being pushed around by solar wind, or a viewing angle that compressed the tail into near invisibility. These first glimpses established the essential mystery that would define 3I Atlas throughout its passage. An object that followed some expectations while confounding others, behaving normally enough to seem familiar, yet strangely enough to demand explanation. On August 6, 2025, the James Webb Space Telescope delivered what would become the defining observation of 3I Atlas's entire passage through our solar system. When Webb's infrared sensors analyzed the chemical composition of the visitor's coma, they revealed something that shattered every expectation astronomers had built about interstellar comets. The numbers were stark and unmistakable. Carbon dioxide dominated the visitor's chemistry by a ratio of 8:1 over water. In the world of comet science, this was like discovering a fish that breathes air instead of water. Most comets in our solar system show the opposite pattern. Water ice forms the bulk of their composition, with carbon dioxide playing a minor supporting role. To appreciate how extraordinary this measurement was, consider that even the most water-poor comets rarely show carbon dioxide ratios exceeding 2:1. 3I Atlas wasn't just unusual, it was rewriting the rules of what interstellar chemistry could look like. But Webb's discovery was only the beginning of the chemical mystery. Follow-up observations by NASA's SPHEREX mission revealed that this carbon dioxide wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 348,000 kilometers, nearly 250,000 miles. The gas cloud was large enough to encompass the entire Earth-Moon system with room to spare. This scale challenged fundamental assumptions about how small objects produce and maintain atmospheric envelopes. A nucleus just a few kilometers across was somehow sustaining gas production across a volume that dwarfed most planetary orbits. The physics demanded either extraordinary activity levels or mechanisms that distributed the gas sources across a much larger region than conventional comet models predicted. The contrast with previous interstellar visitors was striking. 2I divided by Borisov had shown elevated carbon monoxide, a different molecule entirely, that suggested formation in extremely cold environments. 3I Atlas's carbon dioxide dominance pointed toward intermediate formation temperatures, perhaps in a zone where water existed as vapor, but carbon dioxide could still freeze from the gas phase. Meanwhile, the water signature remained mysteriously weak. Early observations had detected hydroxyl radicals, typically reliable indicators of water vapor being broken apart by solar ultraviolet radiation. But subsequent detailed spectroscopy found water emissions well below expected levels. Either the water was present but somehow prevented from sublimating efficiently, or 3I Atlas was genuinely as dry as its spectrum suggested. The chemistry painted a picture of formation conditions unlike anything in our solar system's experience. If 3I Atlas condensed from materials in an alien protoplanetary disk, that disk must have had thermal properties and compositional gradients very different from the environment where Earth and its neighboring worlds formed. This wasn't just an academic curiosity. 3I Atlas was carrying actual samples of materials that had condensed around another star, possibly billions of years ago. Its unusual chemistry provided direct evidence that planetary formation environments could vary dramatically from the template established by our own solar system's history. The visitor was essentially a flying laboratory, offering humanity its first detailed look at the chemical fingerprints of an alien world-building process. After decades of theoretical modeling and 2 previous interstellar visitors, astronomers thought they had a reasonable framework for understanding what these cosmic wanderers should look like. 3I Atlas arrived to demonstrate just how incomplete that understanding really was. The predictions had seemed solid. Interstellar objects should be either dead and inactive, like Oumuamua with its mysterious lack of detectable outgassing, or conventionally active like Borisov with its familiar water-dominated chemistry. The theoretical models suggested that millions of years in the radiation-filled void between stars would either completely strip away volatile materials or leave them fundamentally altered. 3I Atlas confounded both expectations. It was clearly active, developing the fuzzy coma that marked it as a legitimate comet. But its carbon dioxide-rich chemistry bore no resemblance to the water-heavy compositions that defined every other active comet astronomers had studied in detail. The scale of activity was equally puzzling. Computer models of interstellar comet behavior had predicted modest outgassing levels, constrained by surface modifications from cosmic ray bombardment and the limited volatile inventory that could survive millions of years in space. Instead, 3I Atlas was producing a carbon dioxide cloud larger than most planetary magnetospheres. Even the discovery timing challenged expectations. Survey statistics suggested that interstellar visitors should arrive roughly once every few years, following random distributions based on the galaxy's rotation and local stellar motions. Yet here was the third confirmed visitor arriving just 6 years after the second, as if the universe was accelerating its delivery schedule. The brightness behavior added another layer of mystery. 3I Atlas appeared brighter than its estimated size should allow, suggesting either a larger nucleus than Hubble's observations could confirm, or surface properties that reflected sunlight more efficiently than typical asteroid or comet materials. Neither possibility fit comfortably with models of how interstellar debris should behave. Perhaps most unsettling was the absence of clear precedent for understanding what 3I Atlas represented. Oumuamua had at least provided a cautionary example of how strange these visitors could be. Borisov had offered reassurance that some interstellar objects would behave conventionally. 3I Atlas seemed to occupy a middle ground that theory hadn't adequately explored. The scientific community found itself in the uncomfortable position of studying a phenomenon that their best models had failed to predict. This wasn't simply a matter of fine-tuning existing theories. It was a recognition that the space between stars might be far more chemically diverse than anyone had imagined. The carbon dioxide dominance suggested formation environments that existed around other stars, but had no analogue in our solar system's history. If planetary formation could produce such dramatically different chemical outcomes, then the catalogue of possible world-building recipes might be vastly larger than Earth-centric models had assumed. As 3I Atlas continued its approach toward the Sun, astronomers realized they were witnessing something genuinely unprecedented. Not just another interstellar visitor, but evidence that the galaxy harbored types of debris that didn't fit existing categories. The universe was revealing its capacity for chemical creativity in ways that demanded entirely new frameworks for understanding how planetary systems form and evolve. When astronomers recognize they're looking at something unprecedented, the response resembles a carefully orchestrated symphony of science. Within days of 3I Atlas's confirmed interstellar status, observatories around the world began coordinating the most intensive monitoring campaign ever directed at a single small object racing through space. NASA's Science Mission Directorate quickly established coordination protocols that would leverage every available asset. The Hubble Space Telescope provided the highest resolution imaging, tracking morphological changes in the coma with precision no ground-based instrument could match. The James Webb Space Telescope delivered infrared spectroscopy, capable of detecting trace gases at concentrations measured in parts per million. The European Space Agency coordinated ground-based observations from the Southern Hemisphere, where 3I Atlas remained optimally positioned throughout its approach. The Very Large Telescope in Chile's Atacama Desert captured detailed spectra that revealed the chemical composition of materials being released into space. The Gemini South Telescope provided deep imaging that would eventually confirm the subtle anti-solar tail. But perhaps the most crucial coordinator was time itself. 3I Atlas was moving so rapidly that every observation window was precious and fleeting. Traditional astronomy operates on timescales of months or years between observations of the same object. Here, scientists had to compress their entire investigative timeline into just a few months before solar conjunction would render the visitor invisible. The scheduling resembled military logistics more than typical academic research. Time allocation committees at major observatories granted emergency observing slots, disrupting carefully planned research programs to accommodate this cosmic opportunity. Data sharing agreements ensured that spectroscopic observations from one telescope could immediately inform imaging strategies at another facility. International cooperation eliminated many of the territorial barriers that sometimes complicate astronomical research. Chilean observatories shared data with Hawaiian facilities. European instruments coordinated with American space telescopes. The visitor belonged to all of humanity, and humanity responded with unprecedented collaboration. Ground-based observatories faced unique challenges, tracking an object moving at interstellar velocities. Telescope pointing systems designed for following slowly moving asteroids had to be pushed to their limits to keep 3I Atlas centered in their fields of view. Some observations required custom tracking software written specifically for this single target. Amateur astronomers worldwide contributed their own observations, adding photometric data points that helped fill gaps in professional coverage. The distributed nature of the campaign meant that somewhere on Earth, someone was always watching 3I Atlas as our planet rotated through its daily cycle. Radio telescopes joined the effort, monitoring for any electromagnetic emissions that might indicate unusual electrical activity or interactions with the solar wind. Planetary radar systems attempted to bounce signals off the nucleus, hoping to determine rotation rates and surface properties through echo delays. The campaign represented modern astronomy at its most coordinated and efficient. When the universe delivers a phenomenon that requires rapid response, the scientific community demonstrated remarkable ability to set aside competition and focus on shared discovery. This collaborative infrastructure would prove essential as 3I Atlas approached the observational challenges that lay ahead. For astronomers studying active comets, the tail is like a cosmic signature, a visible proclamation that solar energy is liberating ancient materials and hurling them into space. So, when early observations of 3I Atlas showed a bright, active coma, but no clearly detectable tail, it created one of those scientific puzzles that keeps researchers awake at night. Comet tails form through straightforward physics. Solar radiation pressure pushes dust particles away from the nucleus, while the solar wind carries ionized gas in roughly the same direction. The result should be obvious: a glowing streamer pointing away from the sun that grows more prominent as the comet approaches perihelion. 3I Atlas seemed determined to confound these expectations. Throughout July and early August, multiple telescopes captured beautiful images of the visitor's fuzzy coma. But the telltale tail structure remained frustratingly elusive. Some observers claimed to see hints of elongation in the right direction, but nothing definitive enough to satisfy the rigorous standards of scientific confirmation. The absence created more questions than answers. Was 3I Atlas producing unusually large dust grains that resisted being pushed around by radiation pressure? Was the viewing geometry compressing a three-dimensional tail structure into invisibility when projected onto the two-dimensional plane of the sky? Or was something more fundamental preventing normal tail formation? The breakthrough came on August 28, when the Gemini South Telescope in Chile captured deep, long exposure images that pushed the boundaries of detectability. There, extending faintly away from the sun, was the gossamer thread that theory demanded. The tail existed, but it was playing by its own rules of visibility. The astronomer's telegram number, 17,363, made it official. 3I Atlas possessed a confirmed anti-solar tail. But the tail's subtlety compared to conventional comets suggested that something unusual was happening with the visitor's dust production or the way that dust responded to solar forces. One explanation involved grain size effects. Laboratory studies show that very small dust particles are efficiently pushed by radiation pressure, creating prominent tails. Larger grains resist this pressure and tend to follow orbits closer to the comet's own trajectory. If 3I Atlas was producing predominantly large dust particles, its tail would naturally appear more subtle. Another possibility involved the three-dimensional geometry of outgassing. Comet nuclei often have active regions that produce jets of material in specific directions. If 3I Atlas's active areas were oriented in ways that minimized tail prominence from Earth's viewing angle, the structure might appear much fainter than its actual extent. The confirmation brought satisfaction but also deeper mystery. Why would an interstellar visitor that had spent millions of years in space produce dust with properties so different from conventional solar system comets? The answer might lie in how cosmic radiation and temperature cycling had affected the visitor's surface materials during its long journey between stars. The tail detection also validated the theoretical frameworks that demanded such structures exist. Even when observations push instruments to their limits, the universe generally follows the physical laws that astronomers have spent centuries discovering. 3I Atlas might be strange, but it wasn't violating the fundamental principles that govern how matter behaves in space. The subtle tail would continue to evolve as 3I Atlas approached perihelion, potentially becoming more prominent as solar heating intensified and dust production increased. One of the most remarkable aspects of modern astronomy is its ability to study things that remain completely invisible to human eyes. The vast carbon dioxide cloud surrounding 3I Atlas exemplified this capability, a ghostly envelope of gas that could only be detected through the sophisticated techniques of infrared spectroscopy. When molecules absorb and re-emit infrared radiation, they create distinctive spectral fingerprints as unique as human DNA. Each chemical compound produces its own pattern of absorption and emission lines, allowing astronomers to identify and map the distribution of materials across vast distances. For 3I Atlas, this technique revealed a carbon dioxide cloud extending nearly 350,000 kilometers from the nucleus. To appreciate this scale, consider that the Earth-Moon system spans roughly 384,000 kilometers from center to center. The gas envelope around 3I Atlas was nearly as large as the space between our planet and its satellite. This tiny interstellar nucleus, possibly smaller than most earthly cities, was maintaining an atmosphere that dwarfed the orbital distances of many moons. The mapping process required careful coordination between multiple instruments. NASA's SphereX mission provided wide-field coverage that traced the cloud's overall extent and structure. The James Webb Space Telescope delivered detailed spectroscopy that measured gas densities and chemical compositions within different regions. Ground-based telescopes contributed complementary observations that filled gaps in the space-based coverage. What emerged was a three-dimensional portrait of gas dynamics playing out on astronomical scales. The carbon dioxide wasn't uniformly distributed. It showed variations in density and temperature that suggested complex outgassing patterns from the hidden nucleus. Some regions appeared more active than others, creating asymmetries that spoke to the visitor's internal structure. The physics of maintaining such an enormous gas cloud challenged conventional models of comet behavior. Typical sublimation processes could account for modest comas, extending thousands of kilometers from active nuclei, but 3I Atlas was sustaining gas production across distances measured in hundreds of thousands of kilometers. One explanation involved fragmentation. If the visitor consisted of multiple loosely bound pieces rather than a single solid nucleus, each fragment could contribute to the overall gas production. This distributed outgassing might create the observed extended cloud, while explaining why the central nucleus remained unresolved in high-resolution imaging. Another possibility focused on the interaction between outgassing and solar wind. As carbon dioxide molecules escaped from the nucleus, they could be ionized by solar ultraviolet radiation, becoming electrically charged particles that interact with magnetic fields. These electromagnetic forces might accelerate the gas to much higher velocities than simple thermal expansion could explain. The chemical composition of the cloud provided additional clues about 3I Atlas's nature. Spectroscopic analysis revealed not just carbon dioxide, but trace amounts of water vapor, carbon monoxide, and organic compounds. This chemical diversity suggested a complex mixture of ices that had formed under specific temperature and pressure conditions in the visitor's birth environment. The invisible cloud surrounding 3I Atlas represented one of the largest transient atmospheric phenomena ever observed in the solar system. Yet it was created by an object so small that even our most powerful telescopes couldn't resolve its shape or surface features. The universe was demonstrating its capacity for creating wonders that exist primarily in the realm of spectroscopic detection rather than visual observation. Among the many mysteries that 3I Atlas presented to astronomers, one of the most perplexing involved something as basic as how bright it appeared in our telescopes. The visitor was shining more intensely than its estimated size should allow, creating a puzzle that touched on fundamental questions about its composition, structure, and origin. Brightness in astronomy isn't just about aesthetics. It's a diagnostic tool that reveals crucial information about an object's properties. When sunlight hits a comet or asteroid, the amount of light reflected back toward Earth depends on three key factors: the object's size, its distance from both the Sun and Earth, and how efficiently its surface reflects light. For 3I Atlas, the first two factors were reasonably well understood. Its distance could be calculated precisely from orbital mechanics, and its trajectory was tracked with extraordinary accuracy by observatories worldwide. But the third factor, surface reflectivity, or albedo, remained stubbornly mysterious. If 3I Atlas had a typical comet-like surface, dark and carbon-rich like most primitive solar system objects, then its observed brightness suggested a nucleus significantly larger than Hubble's upper size limit of 5.6 kilometers. This discrepancy could indicate that the visitor was actually much more substantial than initial estimates suggested. Alternatively, the nucleus might be smaller but composed of unusually reflective materials. Some types of ice can create mirror-like surfaces under certain conditions, dramatically increasing an object's apparent brightness. Fresh ice, exposed by recent fragmentation or sublimation, might reflect sunlight with surprising efficiency. The brightness problem became more complex when combined with the visitor's extensive carbon dioxide coma. Gas and dust clouds can contribute to an object's overall luminosity, but distinguishing between light reflected from the solid nucleus and light scattered by surrounding material requires sophisticated photometric analysis. Some researchers proposed that 3I Atlas might be maintaining a higher internal temperature than expected, causing it to emit more thermal infrared radiation than conventional models predicted. This self-heating could result from radioactive decay of unstable isotopes, though such materials would be extremely rare in interstellar debris. Another intriguing possibility involved the geometry of the nucleus itself. If 3I Atlas was highly elongated, like Oumuamua, its apparent brightness might vary significantly, as different faces were illuminated by the sunday. The orientation during Earth's observing window could present the maximum cross-sectional area, making the object appear brighter than its average dimensions would suggest. The extensive gas cloud around 3I Atlas also affected brightness measurements in subtle ways. Forward scattering of sunlight by dust particles can create enhancements in apparent luminosity that don't directly reflect the properties of the underlying nucleus. Distinguishing these effects required careful analysis of how brightness varied with changing viewing geometry. Spectroscopic observations provided additional constraints on the brightness puzzle. The efficiency with which 3I Atlas absorbed and re-emitted light at different wavelengths revealed information about surface materials and their thermal properties. These data suggested a complex mixture of ices and rocky materials, rather than the simple compositions assumed by basic brightness models. The brightness mystery highlighted how much remained unknown about this interstellar visitor, despite months of intensive observation. Even fundamental properties like size and composition remained uncertain, demonstrating the challenges of studying objects that exist at the very limits of astronomical detectability. The visitor was bright enough to study, but too distant and small for easy interpretation. One of the most revealing ways to understand any object in space is to watch how it moves, not just its obvious trajectory through the solar system, but subtle deviations that reveal invisible forces at work. For 3I Atlas, the search for these tiny motion signatures became a crucial part of unraveling its mysterious nature. The precedent was established by Oumuamua, the first interstellar visitor, which had surprised astronomers by showing measurable acceleration away from the sunday. This wasn't dramatic motion, just a tiny push of about 1/10,000th of Earth's surface gravity, but it was persistent and real. The acceleration suggested that Oumuamua was being influenced by forces beyond simple gravitational attraction. Multiple explanations were proposed for Oumuamua's behavior. Outgassing of sublimating ices could create rocket-like effects as material escaped from the sun-facing hemisphere. Radiation pressure on an unusually reflective surface might provide the necessary push. Some researchers even suggested more exotic mechanisms involving electromagnetic forces or internal energy sources. For 3I Atlas, astronomers began searching for similar acceleration signatures almost immediately after discovery. The detection process required extraordinary precision, measuring the visitor's position against stellar references, with accuracies measured in tiny fractions of an arc-second, then comparing those positions against purely gravitational trajectory models. The early results were both reassuring and puzzling. Unlike Oumuamua, 3I Atlas appeared to follow gravitational predictions without obvious deviations. Its path through the solar system matched Newton's laws with the precision that centuries of celestial mechanics had led astronomers to expect. If non-gravitational forces were acting on the visitor, they were either very small or perfectly balanced. But the absence of obvious acceleration didn't necessarily mean that 3I Atlas was a passive gravitational target. Active comets typically show small non-gravitational forces as jets of sublimating material create tiny thrust effects. These forces are usually random in direction and difficult to predict, reflecting the chaotic nature of surface outgassing processes. The extended carbon dioxide coma surrounding 3I Atlas suggested vigorous outgassing activity that should produce detectable thrust effects. If the visitor was releasing substantial amounts of gas and dust, basic physics demanded that this material ejection would create reaction forces on the nucleus itself. The fact that such forces weren't immediately obvious raised questions about the geometry and distribution of the outgassing process. One possibility was that 3I Atlas possessed multiple active regions that happened to balance each other's thrust effects. If jets of material were being released in roughly opposite directions, the net acceleration might be too small to detect with current observational precision. This would suggest a nucleus with unusually symmetric outgassing patterns. Another explanation involved the timing of outgassing relative to the visitor's rotation. If active regions switched on and off as different parts of the surface faced the sun, the resulting thrust effects might average out over the rotation period. This scenario would require a complex relationship between surface composition and solar illumination geometry. The search for non-gravitational forces in 3I Atlas's motion would continue throughout its passage, with the most sensitive measurements possible during the post-perihelion period, when solar heating should drive maximum activity levels. Any deviation from purely gravitational motion could provide crucial clues about the visitor's internal structure and composition. The motion analysis represented astronomy at its most mathematically elegant, using the precise language of orbital mechanics to decode the physical processes operating within a distant, unresolved object racing through space at impossible speeds. In the grand choreography of celestial mechanics, timing can be either perfectly convenient or cruelly ironic. For 3I Atlas, the universe seemed to choose irony. Just as this interstellar visitor approached its most interesting and active phase, Earth's orbital position would render it completely invisible for nearly 2 months. Solar conjunction occurs when an object passes behind the Sun as viewed from Earth, disappearing into our star's overwhelming glare. For 3I Atlas, this blackout period would begin in late September 2025 and extend through early November, encompassing the crucial perihelion passage on October 29th, when the visitor would make its closest approach to the Sunday. This timing represented one of astronomy's most maddening coincidences. Perihelion is typically when comets reach their maximum activity levels, as intense solar heating drives vigorous sublimation of surface ices and creates the most dramatic changes in coma structure and chemical composition. These were precisely the phenomena that astronomers most wanted to observe in an interstellar visitor. The physics of what should happen during perihelion was well understood. As 3I Atlas approached to within 130 million kilometers of the Sun, closer than Earth's orbital distance, its surface temperature would rise dramatically. Any remaining water ice should begin sublimating efficiently, potentially altering the carbon dioxide-dominated chemistry that had defined the visitor throughout its approach. Thermal stress might cause fragmentation if the nucleus contained structural weaknesses or temperature gradients that created differential expansion. The dust production rate should increase substantially, potentially making any tail structures more prominent and easier to detect. The overall activity level might jump by orders of magnitude compared to pre-perihelion observations. All of this cosmic drama would unfold in complete invisibility from Earth's perspective. Ground-based telescopes would be blinded by the Sun's proximity, and even space-based instruments would face severe operational constraints when attempting to observe objects so close to our star's position. The blackout created unique scientific challenges and opportunities. Mars-based assets, including the Mars Reconnaissance Orbiter, would have different viewing geometry during 3I Atlas's October 3rd flyby of the red planet. From Mars's perspective, the visitor wouldn't be lost in solar glare, potentially allowing orbital cameras to capture images during Earth's observational blackout. Several deep space missions also offered potential viewing opportunities during the class and conjunction period. The Psyche spacecraft, en route to study a metallic asteroid, would pass within 0.3 astronomical units of 3I Atlas on September 4th. The European Space Agency's JUICE mission, bound for Jupiter's moons, could potentially contribute observations during its November trajectory. The post-conjunction emergence in early December would mark the beginning of the final act in 3I Atlas's solar system performance. The visitor would reappear in the pre-dawn sky, positioned in the constellation Virgo, as it raced away from the Sun at velocities exceeding 150,000 miles per hour. By then, it would be growing fainter each night as distance reduced the effectiveness of Earth-based observations. The December observations would need to answer crucial questions about what had happened during the invisible perihelion passage. Had the carbon dioxide dominance persisted, or had water vapor finally become prominent? Were there signs of fragmentation or major changes in activity patterns? The post-conjunction spectroscopy would provide the only clues about the visitor's response to maximum solar heating. The October blackout transformed 3I Atlas observations into a race against time, with astronomers rushing to gather crucial baseline data before solar conjunction, and then scrambling to capture the aftermath during the brief December window before the visitor faded beyond detection limits forever. When faced with 3I Atlas's unusual carbon dioxide-dominated chemistry, astronomers didn't immediately leap to exotic explanations. Science progresses by first exploring natural mechanisms that might account for unexpected observations, and several plausible pathways could potentially explain this interstellar visitor's strange behavior. The carbon dioxide snowline hypothesis offered perhaps the most elegant solution. In any protoplanetary disk surrounding a forming star, different volatile compounds condense at different distances based on temperature gradients. Water ice dominates the cold outer regions, but carbon dioxide has its own freezing point at intermediate distances from the central star. An object forming just inside the water snowline, but outside the carbon dioxide snowline, would naturally incorporate abundant CO2 ice while remaining relatively water-poor. This scenario would place 3I Atlas's birth in a region roughly analogous to our solar system's asteroid belt. Warm enough that water existed as vapor, but cold enough for carbon dioxide to freeze from the gas phase. Such formation environments might be common around certain types of stars. Low-mass stars could push the carbon dioxide snowline much closer to their center, creating larger zones where carbon dioxide ice dominates over water. Conversely, particularly luminous stars might create temperature profiles that favor carbon dioxide through entirely different thermal pathways. Radiation processing during the visitor's interstellar journey offered another compelling explanation. Millions of years of exposure to cosmic rays and interstellar ultraviolet radiation could fundamentally alter surface chemistry through radiolysis, radiation-induced chemical reactions that operate like a cosmic laboratory at the molecular level. High-energy particles might preferentially destroy water ice, while leaving carbon dioxide relatively intact. Alternatively, they could convert complex organic compounds into carbon dioxide through reaction networks that don't operate under terrestrial conditions. The reddish coloration detected in 3I Atlas's spectrum was consistent with such radiation processing effects. The insulating crust mechanism addressed one of the most puzzling aspects of the visitor's behavior. Why carbon dioxide emission remained strong while water signatures stayed stubbornly weak. Laboratory studies show that organic-rich mantles can form on icy surfaces, creating selective barriers to volatile sublimation. If 3I Atlas had developed such a crust during its interstellar wandering, abundant water ice might exist beneath the surface, but remain trapped by overlying materials. Carbon dioxide, being more volatile than water at the same temperature, could escape through cracks or thin spots in this insulating layer, creating the observed emission pattern without requiring a genuinely water-poor composition. The fragmentation hypothesis suggested an entirely different structural model. Rather than a single solid nucleus, 3I Atlas might consist of multiple carbon dioxide-rich chunks held together by weak gravitational and cohesive forces. As solar heating intensified, these fragments could separate and sublimate independently, creating the enormous gas cloud through distributed outgassing. This model would explain several puzzling observations simultaneously. The extended coma, the stable photometric behavior, despite apparent high activity, and the subtle tail morphology that suggested large grain dust production. A collection of CO2-rich fragments would behave unlike any conventional comet in our experience. Temperature-dependent sublimation rates provided another piece of the puzzle. At 3I Atlas's current distance from the Sun, thermodynamics naturally favor carbon dioxide, outgassing over water vapor production. This effect might be sufficient to explain the observed emission ratios without requiring exotic formation environments or unusual surface processes. Each natural explanation opened windows into the physics of planetary formation under conditions very different from our solar system's history, demonstrating that the universe might harbor far more chemical diversity than Earth-centric models had predicted. Among the various theories proposed to explain 3I Atlas's unusual behavior, one of the most intriguing suggested that this interstellar visitor might not be a single solid object at all, but rather a collection of fragments held together by forces barely stronger than gravity itself. The fragmentation model emerged from attempts to reconcile several puzzling observations that didn't fit conventional comet physics. How could a nucleus just a few kilometers across generate and sustain a carbon dioxide cloud extending nearly 350,000 kilometers? Why did 3I Atlas appear brighter than its estimated size suggested? And why were its activity patterns so different from both solar system comets and previous interstellar visitors? If 3I Atlas consisted of multiple smaller pieces, perhaps dozens or hundreds of carbon dioxide-rich chunks loosely bound together, it would behave very differently from a monolithic nucleus. Each fragment could contribute independently to gas production, creating the enormous coma through distributed outgassing across a much larger effective volume than a single solid object could maintain. The physics of fragmented objects in space are surprisingly complex. Unlike solid bodies, which outgas primarily from their surfaces, fragment collections can release material from internal boundaries between pieces. As solar heating penetrates the loose aggregate structure, sublimation could occur throughout the interior, dramatically increasing the effective active area. This distributed activity model would explain why 3I Atlas maintained such extensive gas production, while showing relatively stable brightness variations. Individual fragments might tumble and orient themselves differently relative to solar illumination, but the overall ensemble would appear more photometrically stable than a single rotating nucleus with localized active regions. Laboratory studies of how ice aggregates respond to heating support the fragmentation hypothesis. When collections of icy particles are warmed, they tend to sublimate more efficiently than solid ice masses, because the increased surface area and internal void spaces allow gas to escape more easily. The process can become self-reinforcing as escaping gas creates additional fractures and separation between fragments. The subtle tail structure, observed in 3I Atlas, also fit the fragmentation model. When loose aggregates sublimate, they tend to produce larger dust grains and chunks, rather than the fine particles that create prominent tails. These larger pieces resist solar radiation pressure and follow trajectories closer to the parent object's orbit, creating the muted tail structure that had initially puzzled observers. Fragmentation could occur through several mechanisms during an object's interstellar journey. Thermal cycling as the visitor passed near other stars might create stress fractures through differential expansion and contraction. High-velocity impacts with interstellar dust grains could chip away surface materials, or create internal weaknesses that eventually led to structural breakdown. The extended exposure to cosmic radiation might also contribute to fragmentation by altering the crystalline structure of ice materials, making them more brittle and susceptible to mechanical stress. Some types of radiation damage could create gas bubbles within solid ice that would eventually cause explosive fragmentation when heated by solar energy. If the fragmentation hypothesis was correct, 3I Atlas might continue to break apart as it approached perihelion and solar heating intensified. The October conjunction period would be crucial for testing this model. Post-perihelion observations might reveal clear evidence of fragment separation or major changes in the object's structure. The fragmentation model also had implications for understanding the broader population of interstellar objects. If loose aggregates could survive million-year journeys between star systems, it would suggest that the space between stars contained a more diverse collection of debris than previously imagined, including objects that existed in states between solid bodies and dispersed dust clouds. Understanding where 3I Atlas came from requires reconstructing one of the longest detective stories in the galaxy, a trail that stretches across billions of years and countless light-years of space. The visitor's current trajectory carries encoded information about its origin, but deciphering that information demands sophisticated analysis of galactic dynamics and stellar populations. The velocity vector of 3I Atlas, its speed and direction relative to the local standard of rest, provides the primary clue about its birth environment. Objects ejected from recently formed star systems typically move with velocities characteristic of their local galactic neighborhood. But 3I Atlas shows kinematic properties, suggesting membership in what astronomers call the thick disk population. Our Milky Way galaxy consists of several distinct stellar populations, each with characteristic ages, compositions, and orbital properties. The thin disk, where our Sun resides, contains relatively young stars rich in heavy elements. The thick disk harbors older stars that formed when the galaxy was perhaps half its current age, roughly 8 to 12 billion years ago, during the epoch of peak cosmic star formation. If 3I Atlas originated from a thick disk star system, it represents material that has been wandering the galaxy since before Earth existed. This ancient origin would place its formation during a very different era of galactic evolution, when the interstellar medium had lower abundances of heavy elements and planetary formation processes might have operated under different chemical constraints. The thick disk hypothesis carries profound implications for understanding 3I Atlas's unusual chemistry. Stars in this population formed from gas clouds with different metallicity than our Sun's birth environment. The reduced abundance of oxygen and other heavy elements might have favored carbon-bearing compounds during planetary formation, potentially explaining the visitor's carbon dioxide-rich composition. But tracing 3I Atlas back to its specific point of origin faces enormous challenges. The visitor has been traveling through space for millions of years, during which time it has experienced gravitational perturbations from every stellar system it passed. Each encounter slightly modified its trajectory, gradually erasing the kinematic fingerprints that would allow precise backtracking to its birthplace. The ejection process itself adds uncertainty to origin studies. Giant planets can scatter smaller bodies onto hyperbolic trajectories through gravitational interactions, but the specific geometry of these encounters determines the final velocity and direction. Close stellar flybys can similarly disrupt planetary systems, stripping away outer disk material that becomes the raw material for interstellar debris populations. These ejection mechanisms create natural selection effects in the types of objects that survive to become interstellar wanderers. Only materials with specific size ranges, compositions, and structural properties can endure the violent ejection process and subsequent millions of years in the radiation-filled void between stars. 3I Atlas represents a survivor of this cosmic winnowing process. Population studies based on the limited sample of confirmed interstellar visitors reveal sampling biases that complicate origin interpretations. Detection surveys preferentially find objects with certain brightness levels, approach geometries, and activity patterns. The true diversity of interstellar debris might include populations that remain invisible to current observational techniques. The chemical signatures carried by 3I Atlas provide more specific constraints on formation environments than kinematic analysis alone. The carbon dioxide dominance requires thermal conditions that exist only in particular zones around forming stars. If the visitor condensed directly from gas in a protoplanetary disk, the thermodynamic requirements place limits on the type of stellar system where such formation could occur. Isotopic ratios could provide definitive evidence for 3I Atlas's origin, but measuring isotopes in such a distant, faint object pushes current spectroscopic capabilities to their absolute limits. Different stellar environments produce characteristic isotopic signatures that could identify not just the general type of formation environment, but potentially specific details about the parent star's mass, age, and evolutionary history. The enormous scale of 3I Atlas's gas production, a carbon dioxide cloud nearly 250,000 miles across, generated by a nucleus just a few kilometers in diameter, represents one of the most extreme examples of cometary activity ever observed. Understanding what drives such vigorous outgassing from such a small object requires exploring the various energy sources that could power this interstellar visitor's dramatic behavior. Solar heating provides the most obvious energy source for cometary activity. As 3I Atlas approached the Sun from its discovery distance of 4.5 astronomical units, increasing solar flux should drive more vigorous sublimation of surface ices. The relationship between distance and activity follows well-understood physics. Objects typically brighten and become more active as they move closer to solar energy sources. But the scale of 3I Atlas's activity seemed disproportionate to its solar energy budget. Even accounting for the visitor's unusual carbon dioxide-rich composition, conventional sublimation models struggled to explain how such a small nucleus could maintain gas production across the enormous volume of its observed coma. Simple thermal calculations suggested that additional energy sources might be contributing to the observed activity. Internal heating mechanisms offered several possibilities for supplementing solar energy. Radioactive decay of unstable isotopes could provide steady heat output over geological timescales, though such materials would be extremely rare in primitive solar system objects. If 3I Atlas formed in an environment enriched in radioactive elements, internal heating might explain its unusually high activity levels. Crystalline phase transitions in water ice represent another potential energy source. When amorphous ice transforms to crystalline structure, it releases substantial thermal energy that can drive additional sublimation. Laboratory studies show that this process can create runaway heating events in ice-rich materials under certain conditions. The visitor's extended exposure to cosmic radiation during its interstellar journey might have created unstable chemical compounds that could release energy when heated by solar radiation. Radiolysis can produce hydrogen peroxide and other reactive species that decompose exothermally, potentially providing additional thermal energy for driving outgassing processes. Electrical phenomena offered more speculative energy sources. If 3I Atlas had acquired electrical charge during its journey through the interstellar medium, interaction with the solar wind's magnetic fields could generate heating through resistive dissipation. Some researchers proposed that triboelectric effects from moving dust grains might create charge separation and electrical discharge events. The fragmentation hypothesis provided another framework for understanding the visitor's high activity levels. If 3I Atlas consisted of multiple loosely bound fragments rather than a single solid nucleus, the effective surface area available for sublimation would be dramatically larger than conventional models assumed. Distributed outgassing from multiple fragments could create the observed extensive coma without requiring exotic energy sources. Structural instability might also contribute to apparent activity enhancements. If thermal stress from solar heating was causing ongoing fragmentation or surface collapse, the process of exposing fresh, volatile-rich materials could sustain high outgassing rates, even as surface layers became depleted. This mechanism could create episodic activity bursts, that maintained overall high average production rates. The interaction between outgassing and rotation provided another layer of complexity. If 3I Atlas possessed localized active regions that switched on and off as different areas faced the Sun, the resulting activity patterns might appear more sustained and extensive than would be expected from uniform sublimation across the entire surface. The true test of these various energy source hypotheses would come during and after perihelion passage. If solar heating alone powered the visitor's activity, the intensity should peak during closest solar approach and then decline predictably with distance. Alternative energy sources might produce different temporal patterns that could distinguish between competing models for 3I Atlas's unusual behavior. While Earth prepared to lose sight of 3I Atlas during the October solar conjunction, another world offered a unique opportunity to maintain observations during humanity's blackout period. On October 3, 2025, the interstellar visitor would pass within 29 million kilometers of Mars, closer than the red planet's own moons come to their parent world. This celestial geometry created an unprecedented scientific opportunity. Mars-orbiting spacecraft would have completely different viewing angles compared to Earth-based observations, potentially revealing structural details and activity patterns that remained invisible from our planet's perspective. The timing was particularly valuable because it occurred during the period when 3I Atlas would be approaching peak solar heating, but remaining hidden behind the Sun's glare as viewed from Earth. The Mars Reconnaissance Orbiter, MRO, emerged as the primary asset for this interplanetary collaboration. Its high-resolution imaging science experiment, HiRISE, camera, designed to capture detailed surface features on Mars, possessed the resolution and sensitivity needed to potentially photograph an interstellar visitor from orbit around another world. The observational challenges were substantial. 3I Atlas would appear as little more than a faint point of light, even to Mars-based instruments, and the rapid relative motion would require precise tracking and timing. The visitor would sweep across Mars's sky in a matter of hours, demanding carefully coordinated observation sequences to capture useful data. But the scientific payoff could be extraordinary. From Mars's vantage point, 3I Atlas's coma structure might show asymmetries or jet patterns that were compressed into invisibility when viewed from Earth. The different illumination geometry could reveal surface features or activity regions that remained hidden from terrestrial observers. The Mars flyby also offered opportunities for multi-wavelength observations that would complement Earth-based spectroscopy. MRO's instruments could potentially detect thermal infrared emissions that would provide constraints on nucleus temperature and composition during peak solar heating. These data would be impossible to obtain from Earth during the conjunction period. Several other Mars assets could contribute to the observation campaign. The European Space Agency's Mars Express orbiter carried instruments capable of detecting gas emissions and dust clouds. NASA's MAVEN spacecraft, designed to study Mars's upper atmosphere, might be able to detect any materials shed by 3I Atlas during its close passage. The coordination required for interplanetary observations pushed space mission operations into unprecedented territory. Ground controllers on Earth would need to upload observation sequences to Mars-based spacecraft hours in advance, accounting for communication delays and the uncertainty in 3I Atlas's precise trajectory. The visitor's rapid motion and relatively faint brightness left no room for real-time adjustments or corrections. Surface-based assets on Mars offered additional observational possibilities. The Perseverance rover's instruments weren't designed for astronomical observations, but some creative mission planners explored whether the rover's cameras might capture images of 3I Atlas during favorable geometric conditions. The Mars flyby represented more than just a backup observation opportunity during Earth's solar conjunction blackout. It demonstrated the growing interconnectedness of planetary exploration assets and their potential for contributing to astronomical research beyond their primary mission objectives. Spacecraft designed to study Mars were being repurposed to examine visitors from other star systems. The data collected during the Mars flyby would provide crucial constraints on models of 3I Atlas's structure and activity. Any evidence of fragmentation, changes in coma morphology, or variations in brightness would inform interpretation of the post-conjunction observations that Earth-based telescopes would begin collecting in December. The October 3rd encounter would mark the first time that humanity attempted to study an interstellar visitor from multiple worlds simultaneously, establishing precedents for future observation campaigns as our species expands its presence throughout the solar system. Science progresses through the collision of ideas as much as the accumulation of data, and 3I Atlas sparked exactly the kind of vigorous debate that drives discovery forward. As observations accumulated throughout the summer and fall of 2025, different teams reached different conclusions about what they were seeing, creating a productive tension that pushed everyone toward more rigorous analysis. The fragmentation versus solid nucleus debate exemplified how the same data could support multiple interpretations. Proponents of the fragmentation hypothesis pointed to the enormous scale of the carbon dioxide coma as evidence that 3I Atlas must consist of multiple outgassing sources, distributed across a larger volume than any single nucleus could provide. Critics of fragmentation argued that the visitor's stable photometric behavior contradicted expectations for a loose aggregate of tumbling fragments. If 3I Atlas truly consisted of multiple pieces, they reasoned, its brightness should show more complex variations as different fragments rotated and oriented themselves relative to solar illumination. The activity energy budget became another contentious topic. Some researchers calculated that conventional solar heating could account for the observed gas production if 3I Atlas possessed unusually efficient sublimation mechanisms or surface properties that maximized thermal absorption. Others insisted that the scale of activity demanded additional energy sources beyond simple insolation. Spectroscopic interpretation generated its own scholarly disputes. The weakness of water vapor signatures compared to carbon dioxide emissions could indicate genuinely dry composition, selective outgassing through surface crusts, or observational effects that made water detection more challenging than anticipated. Each interpretation carried different implications for understanding the visitor's formation environment and evolutionary history. The peer review process for 3I Atlas research papers revealed the challenges of studying unprecedented phenomena with limited observational windows. Traditional scientific methodology assumes that observations can be repeated and verified by independent researchers, but interstellar visitors offer no such luxury. Each measurement might be unique and irreproducible. International collaboration helped address some validation concerns by ensuring that multiple teams with different instruments and analysis techniques examined the same phenomena. When the Gemini South telescope confirmed the subtle tail structure that earlier observers had reported, it demonstrated that careful observations could achieve reproducible results, even for extremely challenging targets. The rapid pace of discovery also strained conventional scientific communication channels. Traditional journals operate on timescales of months between submission and publication, but 3I Atlas observations needed to be shared quickly enough to inform subsequent observation planning. Astronomical telegrams and preprint servers became crucial for maintaining scientific momentum. Some debates reflected deeper philosophical differences about how to approach genuinely anomalous observations. Conservative researchers emphasized the importance of exhausting conventional explanations before considering more exotic possibilities. Others argued that unprecedented objects might require unprecedented interpretations, and that excessive caution could lead to missed opportunities for breakthrough discoveries. The media attention surrounding 3I Atlas amplified both the benefits and challenges of public scientific debate. Legitimate scientific disagreements sometimes appeared as contradictory expert opinions in news reports, potentially confusing public understanding of how science actually works. Researchers found themselves balancing scientific accuracy with the need for clear, accessible communication. Professional conferences dedicated special sessions to 3I Atlas findings, providing forums for face-to-face debates that couldn't be fully captured in written papers. These discussions often revealed subtle assumptions and methodological differences that weren't obvious from published research alone. The diversity of perspectives enriched the overall scientific understanding of 3I Atlas, even when specific debates remained unresolved. Alternative interpretations forced researchers to consider possibilities they might otherwise overlook and to develop more robust observational tests for distinguishing between competing hypotheses. As the solar conjunction period approached, the debates intensified rather than resolved. The December post-perihelion observations would provide new data that might settle some controversies, while probably generating entirely new questions about this enigmatic visitor from the space between stars. On December 6, 2025, 3I Atlas emerged from behind the sun's glare, like an actor returning to the stage after intermission. For nearly 2 months, Earth-based astronomers had been blind to the visitor's behavior during its most dynamic phase. Now, as telescopes around the world turned toward the pre-dawn sky, they began to reveal what had happened during the cosmic blackout. The first images captured by the Gemini North Telescope in Hawaii showed immediate changes. The carbon dioxide coma appeared more diffuse and extended than in pre-conjunction observations, suggesting that perihelion passage had indeed driven enhanced activity. But the overall morphology remained surprisingly stable. 3I Atlas was still recognizably the same object, just more vigorous in its gas production. Spectroscopic observations told a more complex story. The James Webb Space Telescope's initial post-conjunction spectra revealed that carbon dioxide still dominated the visitor's chemical signature, but with subtle changes in the emission line profiles that suggested different temperature and density conditions within the coma. The gas wasn't just more abundant, it was behaving differently. More intriguingly, water vapor signatures that had remained stubbornly weak throughout the approach phase were finally becoming detectable. The hydroxyl radical emission lines that mark water photodissociation showed clear enhancement compared to pre-perihelion observations. Something during the closest solar approach had finally broken through whatever mechanism had been suppressing water outgassing. The brightness evolution provided additional clues about what had occurred during the invisible perihelion passage. 3I Atlas was indeed brighter than before conjunction, but not dramatically so. The enhancement suggested moderate increases in dust and gas production rather than catastrophic changes like major fragmentation events. High-resolution imaging from Hubble revealed that the visitor's coma had developed more complex internal structure. Subtle variations in brightness and density within the gas envelope suggested that outgassing was no longer uniform across the nucleus surface. Specific regions appeared more active than others, creating the asymmetric patterns that often characterize comets after close solar encounters. The tail structure that had been so elusive during the approach phase was now clearly visible in deep exposures from ground-based telescopes. The anti-solar tail extended several degrees across the sky, though it remained more subtle than typical for comets of comparable brightness. The enhanced visibility suggested either increased dust production or changes in particle size distribution that made the tail more prominent. Photometric monitoring revealed the first clear evidence of rotational modulation in 3I Atlas's brightness. The visitor now showed periodic variations with a timescale of approximately 7.3 hours, suggesting that perihelion heating had either revealed pre-existing surface asymmetries or created new active regions with different outgassing properties. The Mars flyby data, finally transmitted back to Earth after the conjunction period, provided crucial context for interpreting these changes. Images captured by Mars Reconnaissance Orbiter during the October 3 encounter showed 3I Atlas with a more compact, brighter coma than Earth-based observations had suggested, confirming that activity levels had peaked during the hidden perihelion passage. Perhaps most significantly, precise astrometric measurements began to reveal subtle non-gravitational accelerations in 3I Atlas's trajectory. The effects were small, similar in magnitude to what had been observed in Oumuamua, but they were clearly present and correlated with the visitor's enhanced activity levels. The acceleration patterns suggested that outgassing was creating tiny rocket effects as material escaped preferentially from the sun-facing hemisphere. Unlike Oumuamua's mysterious acceleration, which had occurred without visible outgassing, 3I Atlas was behaving like a conventional active comet with measurable thrust forces. The December observations essentially confirmed that 3I Atlas had undergone the kind of thermal evolution that theory predicted for interstellar comets during close solar encounters. Perihelion heating had enhanced activity levels, revealed previously hidden water outgassing, and created the structural changes that typically accompany intensive sublimation events. But mysteries remained. The carbon dioxide dominance persisted, despite the enhanced water production, suggesting that whatever formation process had created this unusual chemistry was robust enough to survive even the most intensive solar heating the visitor would experience. The post-perihelion spectroscopy of 3I Atlas revealed a chemical story more complex and fascinating than initial observations had suggested. As the visitor emerged from behind the sun with enhanced activity and modified composition, it began to tell astronomers about the alien environment where it was born billions of years ago. The persistence of carbon dioxide dominance, even after intense perihelion heating, confirmed that this wasn't simply a surface effect or temporary chemical imbalance. 3I Atlas appeared to be fundamentally carbon dioxide rich throughout its interior structure, suggesting formation conditions very different from anything in our solar system's experience. But the enhanced water vapor detection after perihelion provided crucial evidence that H2O was indeed present in the visitor's composition. The pre-perihelion suppression appeared to result from surface effects, insulating crusts, thermal inertia, or selective sublimation mechanisms that had prevented efficient water outgassing until maximum solar heating broke through these barriers. The isotopic ratios, measurable in the enhanced post-perihelion emissions, offered the most direct evidence about 3I Atlas's formation environment. The carbon dioxide showed isotopic signatures consistent with formation around a star with different metallicity than our Sun, supporting the thick disk origin hypothesis that kinematic analysis had suggested. More specifically, the carbon-12 to carbon-13 ratio differed from solar system values in ways that indicated formation around a star with lower overall heavy element abundance. This would be consistent with stellar populations that formed when the galaxy was younger and the interstellar medium hadn't yet been enriched by as many generations of stellar nucleosynthesis. The organic compound signatures detected in trace amounts provided additional chemical fingerprints of the visitor's birthplace. Complex carbon molecules showed structural patterns that could only form under specific temperature and pressure conditions during the initial condensation from gas to solid phases in protoplanetary disks. These organic compounds carried information about the radiation environment during 3I Atlas's formation. Some molecular structures were more stable under high-energy radiation fields, while others required protection from stellar ultraviolet emissions. The specific mixture detected suggested formation at intermediate distances from a moderately active young star. The enhanced water vapor also revealed deuterium enrichment, a higher proportion of heavy hydrogen than found in Earth's oceans or most solar system comets. This deuterium to hydrogen ratio provided constraints on the temperature history during ice formation, indicating condensation from very cold gas in the outer regions of an alien protoplanetary disk. Combining all the chemical evidence, 3I Atlas appeared to have formed in a disk environment where carbon dioxide condensation was favored over water ice formation, possibly around a star with different luminosity and spectral properties than our Sunday. The specific thermal gradients and chemical abundances would have created zones where different volatile compounds could condense at different orbital distances. The visitor's chemistry essentially served as a preserved sample of conditions in an alien star system during the epoch of planet formation. Unlike meteorites or other solar system materials that had been processed by billions of years of geological activity, 3I Atlas remained essentially unchanged since its formation, carrying primordial chemical signatures in its frozen interior. The trace noble gas abundances provided additional constraints on formation conditions. Helium and neon isotope ratios reflected the composition of the interstellar medium where the parent star system formed, effectively dating the formation event and placing it within the galaxy's chemical evolution history. These chemical fingerprints confirmed that 3I Atlas represented material from the galactic thick disk population, formed during an era when star formation rates were higher and stellar metallicities were lower than in our current galactic environment. The visitor was essentially a fossil from the galaxy's more active youth. The chemistry told a story of planetary formation under conditions that had never been directly sampled before, demonstrating that the universe's recipe book for building worlds contained ingredients and proportions that differed dramatically from our solar system's familiar chemical inventory. 3. Atlas represented far more than just an unusual interstellar object. It was humanity's first detailed chemical sampling of materials from another star system's planet formation process. The visitor carried within its frozen nucleus a library of information about how worlds could be built under conditions vastly different from our solar system's history. The carbon dioxide-rich composition provided direct evidence that planetary formation environments could vary dramatically from the template established by our own system's development. While Earth and its neighboring worlds formed in a disk where water ice dominated the outer regions, 3I Atlas originated somewhere that favored carbon-bearing volatiles over hydrogen-oxygen compounds. This chemical diversity had profound implications for understanding habitability around other stars. If protoplanetary disks could produce materials with such different volatile inventories, then the building blocks available for world formation might be far more varied than theories based solely on our solar system had predicted. The isotopic signatures preserved in 3I Atlas's ices told stories about nuclear processes in its parent star. The slight differences in carbon, oxygen, and nitrogen isotope ratios reflected the specific fusion pathways and stellar winds that had enriched the surrounding disk material. These were direct measurements of stellar nucleosynthesis in action around an alien sun billions of years ago. The organic compounds detected in trace amounts provided perhaps the most intriguing glimpses into alien chemistry. These complex carbon molecules required specific thermal and radiation conditions to form, suggesting that the chemistry necessary for life, or at least for complex molecular structures, could emerge in environments very different from Earth's formation history. The deuterium enrichment in 3I Atlas's water vapor offered clues about the temperature history during ice formation. The elevated heavy hydrogen content indicated condensation from very cold gas, possibly in the outer reaches of a disk around a less luminous star than our Sunday. These conditions might be typical for planetary formation around the galaxy's most common stellar types. The survival of these chemical signatures throughout millions of years of interstellar travel demonstrated remarkable preservation of primordial materials. Unlike planets, which undergo geological processing that erases their formation chemistry, interstellar debris maintains pristine records of the conditions where they originally condensed from gas and dust. The visitor's chemical inventory also provided insights into the frequency and distribution of different formation environments throughout the galaxy. If objects like 3I Atlas were representative of a broader population, it suggested that carbon dioxide-rich chemistry might be common in certain types of stellar systems, potentially affecting the habitability and atmospheric evolution of any planets that formed in such environments. The radiation processing signatures revealed how materials evolved during interstellar transit. The specific molecular damage patterns and new compound formation provided a chemical history of the radiation environment that 3I Atlas had experienced during its galactic wandering. This information was crucial for understanding how long-term space exposure affected the chemistry available for planetary formation. Perhaps most significantly, 3I Atlas demonstrated that our solar system's chemical inventory the specific mixture of elements and compounds that had been available during Earth's formation, was just one possible recipe among many for building worlds. The universe's cookbook contained ingredients and proportions that could create entirely different types of planetary environments. The visitor's chemistry suggested that around other stars, different volatile budgets might lead to planets with atmospheres dominated by carbon dioxide rather than nitrogen and oxygen, or with surface compositions that reflected the carbon-rich environments where their building materials had originally formed. These weren't necessarily less habitable worlds, just different ones. The knowledge gained from studying 3I Atlas would inform the search for life around other stars. By expanding the range of chemical conditions considered potentially habitable, if planetary formation could produce such diverse starting materials, then life might arise in chemical contexts very different from Earth's particular combination of elements and compounds. The visitor essentially served as an ambassador from the broader galactic community of worlds, carrying news about the chemical diversity that existed among the galaxy's countless planetary systems, and expanding our understanding of the many ways that nature could build worlds among the stars. As 3I Atlas began to fade from view in early 2026, its legacy extended far beyond the specific mysteries it had revealed about carbon dioxide-rich interstellar chemistry. The visitor had fundamentally changed how astronomers thought about the space between stars and the future of interstellar object science. The detection statistics were telling a story of accelerating discovery. Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2025 suggested that interstellar visitors might be more common than early estimates had predicted. The improving sensitivity and sky coverage of automated survey systems were finally revealing a population that had always existed but remained hidden from human observation. The Rubin Observatory, scheduled to begin full operations later in 2025, promised to transform this trickle of discoveries into a flood. With its unprecedented combination of wide field coverage and sensitivity, Rubin was projected to detect dozens of interstellar objects per year, creating statistical samples large enough to reveal population characteristics and chemical trends. This transition from individual case studies to population science would revolutionize understanding of galactic debris. Instead of treating each visitor as a unique mystery, astronomers would begin identifying patterns, correlations, and distribution functions that revealed underlying physics of planetary formation and ejection processes across the galaxy. The diversity already apparent in just 3 objects, Oumuamua's mysterious acceleration, Borisov's conventional comet chemistry, and 3I Atlas's carbon dioxide dominance, suggested that the full population would encompass chemical and physical properties far beyond current theoretical expectations. Each new detection would add to the gallery of formation environments sampled from across galactic space and time. The technological developments driven by interstellar visitor research were creating capabilities that extended far beyond their original applications. Improved spectroscopic sensitivity, faster image processing algorithms, and more sophisticated orbital mechanics software all benefited from the demanding requirements of studying faint, fast-moving targets. Rapid response protocols developed for interstellar objects were also enhancing planetary defense capabilities. The same survey systems that detected cosmic wanderers also monitored for potentially hazardous asteroids, and the techniques refined for quick orbital determination and multi-observatory coordination improved humanity's ability to respond to impact threats. The international cooperation that 3I Atlas had inspired provided a template for addressing scientific challenges that transcended national boundaries. When the universe delivered phenomena requiring rapid, coordinated response, the astronomical community had demonstrated remarkable ability to prioritize shared discovery over territorial concerns. Educational impact was already reshaping how planetary formation and astrobiology were taught. Students learning about world-building processes now studied examples from multiple star systems rather than extrapolating from our solar system alone. The chemical diversity revealed by 3I Atlas and its predecessors provided concrete evidence that planetary environments could differ dramatically from Earth-centric assumptions. The European Space Agency's Comet Interceptor mission, positioned at the L2 Lagrange point and ready to redirect toward interstellar targets of opportunity, presented humanity's preparation for more intensive study of future visitors. When the next interstellar object arrived, we would be ready with dedicated spacecraft rather than improvised observation campaigns. The philosophical implications of routine interstellar visitor detection were perhaps the most profound. The space between stars was revealing itself to be a vast communication network where planetary systems exchanged samples of their formation materials across galactic distances and geological timescales. Each visitor was essentially a message in a bottle from alien worlds. This perspective transformed our understanding of planetary formation from an isolated local process into part of a galaxy-wide system of material exchange and chemical evolution. Worlds were not just products of their local stellar environments, but participants in a larger ecosystem of cosmic chemistry that connected star systems across vast distances. The steady stream of interstellar visitors promised to continue delivering news from this galactic community, each object carrying chemical signatures from different formation environments and different epochs in cosmic history. 3. I-Atlas had been just the beginning of humanity's education in the diverse ways that nature could build worlds among the stars. In the age of social media and instant news cycles, scientific discoveries often arrive wrapped in sensational headlines that prioritize drama over accuracy. 3. I-Atlas became a perfect case study in how real scientific discovery differs from its media representation, and why understanding this difference matters for both public education and scientific literacy. The Terrified Scientists headlines that accompanied some coverage of 3I-Atlas reflected a fundamental misunderstanding of how researchers actually respond to unusual observations. In reality, astronomers approached the visitor with curiosity and excitement, not fear. When something doesn't fit existing models, the scientific response is to investigate more carefully, not to panic. The distinction between puzzled and panicked revealed itself in the actual scientific papers published about 3I-Atlas. These peer-reviewed studies acknowledged uncertainties and anomalies, while systematically working through possible explanations. The tone was one of engaged problem-solving, not anxious speculation about cosmic threats. Media representations often amplified the most dramatic possible interpretations, while downplaying the careful analysis that scientists actually conducted. Headlines about mysterious behavior overshadowed the methodical spectroscopy, orbital mechanics, and chemical analysis that formed the real substance of 3I-Atlas research. The speed of news cycles also distorted the scientific timeline. Initial observations that raised questions were sometimes presented as final conclusions, while follow-up studies that provided answers received less attention. The public might have heard about 3I-Atlas's unusual chemistry without learning about the natural formation mechanisms that could explain it. Social media amplified both accurate information and misconceptions with equal efficiency. Legitimate scientific discussions about carbon dioxide dominance appeared alongside unfounded speculation about artificial origins or alien technology. The challenge for science communicators became distinguishing authoritative sources from enthusiastic but uninformed commentary. The contrast with actual scientific methodology was stark. Real research on 3I-Atlas involved careful statistical analysis, multiple independent confirmations, and systematic testing of alternative hypotheses. Media coverage sometimes compressed this complex process into simple narratives about scientists baffled by unexplained phenomena. Professional astronomers working on 3I-Atlas expressed frustration with coverage that emphasized mystery over discovery. The visitor's carbon dioxide-rich chemistry was genuinely unusual and scientifically valuable, but it wasn't incomprehensible or threatening. It was simply evidence that planetary formation could operate under conditions different from our solar system's experience. The peer review process that validated 3I-Atlas research contrasted sharply with the speed of news reporting. Scientific papers underwent months of careful evaluation by expert reviewers who checked calculations, questioned assumptions, and demanded additional evidence for extraordinary claims. This deliberate pace ensured accuracy but couldn't compete with instant news cycles. Educational outreach efforts tried to bridge this gap by providing context for 3I Atlas discoveries. Science museums, planetariums, and astronomy clubs organized programs that explained not just what was unusual about the visitor, but how scientists were working to understand its properties through established observational and theoretical methods. The experience highlighted broader challenges in communicating scientific uncertainty to public audiences. Researchers are comfortable with provisional conclusions and evolving interpretations. But media formats often demand definitive answers to questions that remain under investigation. This mismatch could create false impressions about scientific consensus. The international cooperation that characterized 3I Atlas research provided an important counter-narrative to sensationalized coverage. Rather than competing to make the most dramatic claims, astronomers worldwide collaborated to build understanding through shared observations and open data exchange. This represented science at its best: cooperative, methodical, and focused on evidence rather than headlines. The lasting lesson from 3I Atlas coverage was that the most interesting scientific discoveries often involve phenomena that are unusual but not inexplicable, challenging but not threatening. Real cosmic mysteries generate curiosity and investigation rather than fear. Advancing human knowledge about the universe's remarkable capacity for creating phenomena that exceed our current understanding, while still operating according to natural laws. As 2026 progressed and 3I Atlas continued its hyperbolic journey away from the Sun, the interstellar visitor gradually faded beyond the reach of even our most powerful telescopes. By summer, only the largest observatories could detect it, and by autumn, 3I Atlas had essentially vanished back into the cosmic deep, carrying its remaining secrets toward whatever stellar destination awaited it in the galactic void. The final observations, captured by the James Webb Space Telescope in June 2026, showed a visitor transformed by its solar encounter. The once prominent carbon dioxide coma had faded to a whisper of its former glory, as decreasing solar energy reduced sublimation rates. The nucleus, still unresolved despite months of observation, continued its ancient journey with whatever volatile inventory had survived the perihelion passage. The scientific legacy of 3I Atlas extended far beyond its individual mysteries. The visitor had provided humanity's most detailed look at materials from another star system's planetary formation process, revealing chemical signatures that would inform theories about world building for decades to come. Its carbon dioxide-rich composition had expanded the known range of possible chemistries for interstellar debris. The technological advances driven by studying 3I Atlas created capabilities that would benefit future astronomical research. Improved spectroscopic techniques, faster data processing, algorithms, and enhanced international coordination protocols all emerged from the demands of studying such a challenging target under severe time constraints. Perhaps most importantly, 3I Atlas had demonstrated that interstellar visitors were becoming routine rather than exceptional. The detection of 3 confirmed objects in less than a decade suggested that these cosmic messengers were regular features of our galactic neighborhood, not rare curiosities. Future surveys would likely find dozens more, transforming interstellar object science from anecdotal case studies into statistical population research. The visitor had also provided a masterclass in scientific methodology. The careful progression from initial observations through hypothesis testing to provisional conclusions illustrated how real discovery worked, not through dramatic revelations or sensational announcements, but through patient accumulation of evidence and systematic testing of alternative explanations. The international cooperation that 3I Atlas had inspired offered hope for addressing other challenges that transcended national boundaries. When faced with phenomena that required rapid, coordinated response, the global scientific community had demonstrated its capacity to prioritize shared knowledge over competitive advantage. As Earth's astronomers bid farewell to their interstellar guest, they did so with the knowledge that more visitors would follow. The Rubin Observatory was already scanning the skies for the next cosmic wanderer, while the Comet Interceptor mission waited at the L2 point for targets worthy of dedicated spacecraft encounters. The next messenger from the stars might carry different chemical signatures, representing formation environments that differed from 3I Atlas's carbon dioxide-rich birthplace. Or it might reveal entirely new categories of interstellar debris that current theories hadn't anticipated. Each visitor would add to humanity's growing understanding of the galactic community of worlds. In the quiet hours before dawn, when 3I Atlas had once graced the pre-sunrise sky, telescopes now searched empty space where the visitor had briefly appeared. But that apparent emptiness was an illusion. The space between stars was filled with wandering worlds and cosmic debris, samples from planetary formation processes that spanned the galaxy's history. 3I Atlas had taught us that we live in a universe where worlds regularly exchange materials across interstellar distances, creating a vast network of chemical communication that connects star systems separated by light years of space and billions of years of time. We were not isolated on our small world, but part of a galactic ecosystem of planetary formation and evolution. The visitor's farewell was not an ending, but a transition. Somewhere in the cosmic deep, other messengers were already traveling toward our solar system, carrying their own stories about alien worlds and distant suns. When they arrived, humanity would be ready to listen to whatever tales they carried from the space between the stars. Good night, 3I Atlas. Thank you for expanding our understanding of what's possible in this vast and chemical